Alright guys, welcome to this page of the notes, and what we're going to do here is we're going to take a look at what's known as Descartes' Rule of Signs. Now, I need to say this before we go over Descartes' Rule of Signs, and it's this. If you, not every algebra textbook talks about Descartes' Rule of Signs. When it comes to polynomials, all of them will cover the fundamental theorem of algebra. Every algebra book will have the remainder theorem and the factor theorem, right? Every algebra textbook, when it comes to polynomials, talks about those things. I actually have several college algebra textbooks where Descartes' Rule of Signs is never mentioned. And it's for this reason. Descartes' Rule of Signs is going to give us information that either is not really important when it comes to factoring or finding the zeros of a problem, or quite frankly, it gives us information we could find by another method. Now, because it's covered in the textbook that I'm using with my classes, I'm going to go over it just for completeness sake, and because I want you guys to be prepared and have sort of experience everything that's in your textbook. But I will say this, when it comes to polynomials, if you're only going to take away the major highlights, fundamental theorem of algebra, factor theorem, remainder theorem, those should be your takeaways. The Descartes' Rule of Signs in the grand scheme of polynomials is not really that important. Like I said, there are other ways to arrive at exactly what we're going to do here other than Descartes' Rule. The reason I'm going to go over it is it's actually pretty quick. It's very simple. It won't take us long to go over. So let's jump right into it and look at Descartes' Rule. Here's what I want to do. What you're going to do actually in Descartes' Rule is it's based on that idea, if you guys remember when we graphed polynomials and you set up the xy table. And when you set up that xy table, you know that you have an x-intercept whenever you see a change in sign, right? Whenever the y values, the range values go from being positive to negative, you know you must have crossed the x-axis. Or vice versa, whenever the range values go from being negative to being positive, you know you must have crossed the x-axis, and we were able to find consecutive integers. Descartes' Rule of Signs is based on that idea, but instead of setting up an xy table, we're just going to look directly at the polynomial, all right? And so here's the way it's going to work. Descartes' Rule of Signs says this: as long as your polynomial is in standard form, right? It's arranged in descending order of powers, right? Not every power has to be there, right? You don't need placeholders. Don't worry about that. Just the polynomial that you've been given in descending order. You only need placeholders when doing algebraic division or synthetic division. So don't worry about the placeholders. They just need to be in descending order. Then here's what he says. The number of positive real roots is equal. The number of positive real roots is the number of changes in sign of the coefficients, or, right, it's either equal to that or less than that number by an even amount, which I know seems kind of wordy. Just hang in there with me for a second. I'll show you exactly what it means. So here's what I've got for you. I've got a polynomial for you right here, okay? We're going to go through and we're going to look for the number of positive real roots by counting the number of sign changes in the leading coefficients. I have a positive 1 as a leading coefficient. My next leading coefficient is a positive 5. Do I have a sign change? No, because they're both positive. Plus 1, plus 5. No sign change. So then I go positive 5 to a positive 7. Do I have a sign change? No, no sign change. So that doesn't count. Positive 7 to a negative 1. That is a sign change, and so that is going to count as 1 real zero. So there's 1. I then have negative to positive. That is another sign change. So that is going to count as another real positive root. Positive to negative, another sign change, and then yet another one there. Go ahead and count up all of your sign changes. 1, 2, 3, 4. I have 4 sign changes. So these are going to be real positive roots. And I'm going to make myself a little table. I could have as many as 1, 2, 3, 4 positive real roots. I could have as many as 4, right? That's what this says. The number of positive real roots is the number of changes in sign of the coefficients. Or it is less than that number by an even amount. So if I could have 4 positive real roots, or something less than that by an even amount, well, 4, what are even numbers less than 4? Well, 2 or 0. 2 or 0, right? I can't do 3 because 4 minus 3 is 1, and that's not an even number. And I can't do 1 real positive root because 4 minus 1 is 3, and 3 is not an even number, right? It has to be less than whatever the number of sign changes is by an even amount, right? By an even amount. So 4, 2, and 0 are my possibilities. We'll come back to this in just a second. We're going to continue with Descartes' rule of signs with now the negative real roots right here. The number of negative real roots Number of negative real roots is the number of changes in sign of the coefficients of the terms p of negative x. And I'll tell you what that means here in just a second. Or again, same thing, or less than that by an even amount. So here's what we're going to do. It's the exact same polynomial, guys. Please look. I'm not changing problems on you. See, same polynomial here as here. Same polynomial. I found the real positive roots up here. I'm going to find the real negative roots down here for the exact same polynomial. Now, here's what this little bit right here means. What you need to do is whatever the polynomial is you've been given, first, again, it's got to be in standard form, descending order of power, and you need to plug in a negative x as your domain value for every single variable in the polynomial. So you do have a little bit of algebra you need to do for Descartes' rule of signs for negative real roots. And it's actually just this simple. Since my polynomial is f of x, I'm going to do f of negative x. I need to plug a negative x in as my domain value. Well, that means I'm going to have a negative x to the 6th plus 5 times a negative x to the 5th plus 7 times a negative x to the 4th minus negative x to the 3rd plus 6 times negative x squared minus 2 times a negative x plus 4. Apologize, guys, I'm squeezing over there, but I think that's probably pretty clear. Again, all I've done, thanks to Descartes' rule of signs, which tells me, go ahead, plug in a domain value of negative x. So I plug in that domain value everywhere I had an x in my original polynomial. Now we're going to go through and do just a little bit of really simple algebra, and this is very, very simple algebra. You guys should remember, anytime you have a negative number raised to an even power, negative number raised to an even power, the result is always going to be positive every single time. Go ahead and try a bunch of them on your calculator, right? Do a negative 3 squared, a negative 3 to the 4th, negative 3 to the 6th, negative 3 to the 8th, right? Every time you do a negative number raised to an even power, the answer will always be positive. Always, always, always. Also, the other side of that coin, anytime you take a negative number, raise it to an odd power, you're always going to get a negative answer. Always, every time. Try it. Do negative 3 raised to the 3rd power, negative 3 raised to the 5th power, negative 3 raised to the 2nd. It'll always come out to be negative. So we're going to do a little bit of really simple algebra here, and it's this. Negative number raised to an even power is going to come out to be positive. So that goes back to a positive x to the 6th. A negative x raised to an odd power is going to stay negative. So this will be a negative x to the 5th, and a negative times a positive is a negative. So this becomes a negative 5x to the 5th. Why? Because the negative number to an odd power will be negative. Negative times a positive is negative. All right, I have a negative number raised to an even power. That's always going to come out to be positive. Positive times a positive, that stays positive. So that's going to be a 7 x to the fourth. And we just keep going. Negative number, odd power, that's going to be negative. But a negative times a negative is positive. So plus x to the third. Okay. Next one, negative number, even power, that's going to come out to be positive. Positive times a positive is positive. Plus x squared. Sorry, plus 6x squared. And then the next one, I have a negative raised to the first power, of course, is negative. Negative times a negative is positive. Plus 2x, and then plus 4, because I don't have any x's attached to that 4, it's just a constant. Now that I've gone ahead and taken care of that, I've now given myself the polynomial with the domain value of negative x. Count the sign changes. Here we go. Positive to negative, that's 1. Negative to positive, that's another one. Positive to positive, nope. Positive to positive, nope. Positive to positive, positive, positive. Okay, so that's it. Those are my only two, and so now I make my list. This is going to be real, negative, roots. And here's what I've got. I have two sign changes, so that means at most I will have two negative real roots. Two negative real roots. But Descartes' rule says it could be less than that number by an even amount, which means my only other option is 0. So here's what I've got so far. Descartes' rule is as simple as this. Count the number of sign changes on the polynomial you've been given. That'll give you the real positive roots, or less than that by an even amount. And then you're going to go ahead and transform the polynomial by plugging in a domain value of negative x. Do a little bit of simple algebra. Count the sign changes again. And that'll give you the negative real roots. Right? So what we'll do is head on over to the next page of the notes. We'll try a couple more of these and put it all together in one example problem. So I'll meet you over on the next page.